The AAIB detectives have run out of suspects.
There was no clear explanation. Nothing that you'd seen before.
It's not giving me pen.
In any aeroplane, let alone the 777, could have explained this.
Now they turn away from the clues they have to those they don't.
Phil started coming out of a mantra, which was a quote from Sherlock Holmes.
Whatever is left, however improbable, must be the cause.
Has to be.
In this case, we always kept coming back to what's there, what could have been there that's not there now. And we come back to ice.
Suspicion that the cause of the accident was ice grew stronger and stronger.
But investigators are faced with a nearly impossible task. How can they prove that ice had brought down the plane when the evidence they need would have melted by the time they arrived? 3 months after the crash, Brian McDermott flies to Seattle to work with engineers at Boeing, the company that built the 777. If ice brought down Flight 38, they need to prove how and why.
We took the pipes from the right side of the fuel system, and those pipes and those couplings were used on the test rig at Boeing.
Ice in the fuel lines has long been a concern for jets of all kinds. But decades ago, engineers found an ingenious way to deal with the ice forming in the fuel of passenger jets. The heart of the system is the fuel oil heat exchanger, or FOHE. Cold fuel runs through thin tubes, which are surrounded by the hot oil used to lubricate the engines.
The purpose of a fuel heater is to heat the fuel up to prevent icing of the delicate fuel control system.
The FOHE is designed to prevent exactly the problem investigators suspect crippled Flight 38. But it's also a potential bottleneck in the system.
During the fuel testing, we were looking to establish where we could get a restriction that would restrict the fuel flow to 6,000 pounds per hour. And the only place that we could get such a restriction occurring was on the face of the fuel oil heat exchanger.
Investigators have to prove 3 things. First, that substantial amounts of ice can accumulate inside the fuel pipes. Second, that the ice can suddenly be released. And finally, prove that it can block a device specifically designed to melt it.
We use different methods of controlling the environment around the pipes that range from dry ice to cold fuel and to hot air to simulate the environment around the pipes that the aircraft experienced during the flight.
After each fuel cooling test, investigators look inside the pipes for ice. But they can never get much ice to form, let alone block the fuel lines.
And the fuel temperature was minus 30 degrees centigrade. Very little ice would stick to the inside of the fuel pipes.
Investigators know the temperature on the accident flight didn't get much colder. So how had the ice formed?
We still hadn't answered the question of where does the ice come from in the first place? And indeed, was it ice? Or was there something else that we've missed?
Surprisingly, when the fuel temperatures are warmer, the breakthrough arrives.
If you have water in the fuel, then that water will freeze and form ice crystals. And then when the temperature gets to about minus 20 degrees centigrade, then those ice crystals will start to stick together and will also stick to the inside of the pipes.
Below minus 20, any ice crystals in the fuel are too cold to attach to the pipes. But in the sticky range, between minus 20 and minus 8 centigrade, slushy ice forms and sticks to the sides of the fuel pipes.
So when we demonstrated that ice could actually build up and grow onto the walls of the fuel pipes, there was a certain amount of surprise as to how much could actually grow.
Oh, now we're getting somewhere.
Well, the question for us at this stage was, how could that ice come off the pipes?
Investigators think they have the smoking gun.
Right.
But they still can't prove how a small bit of ice could bring down a $200 million plane. They continue analyzing thousands of comparative flights to see what made Flight 38 unique. But after 7 months, they still can't crack the case.
from 35,000 Rolls-Royce powered flights, it was less than 1% that had the same features as the accident flight.
Then, on November the 26th, 2008, more than 10 months after the crash, the importance of finding an answer is underscored when the elusive culprit strikes again. Another 777 runs into trouble 39,000 feet above the United States, when one of its engines simply stops working.
Fortunately, in that case, the engine recovered and the aircraft landed safely at Atlanta.
Even though it didn't result in an accident, it reinforces concerns that there's a potentially dangerous flaw on every 777 around the world. The incident captures the attention of the British Airways crash investigators.
The Delta Shanghai flight really was investigated with huge interest. The engines were Rolls-Royce engines of the same type. So they immediately went looking for evidence of the same problem.
And in fact, they do find important similarities between the Delta airliner and British Airways Flight 38.
The aircraft had operated a long sector from Shanghai in China to Atlanta. The fuel temperatures were within the sticky range that we had defined during the research. We were able to see that the reaction of the engine was very similar to that of the 777 at Heathrow.
Later examination of the Delta flight shows no evidence of any electronic, mechanical, or fuel system problems, strongly suggesting that the culprit was indeed ice.
When we heard about the Delta flight, we were more convinced than ever that we were on the right track.
McDermott and the investigators at Boeing in Seattle continue their testing. It's been a year since the accident, and the problem hasn't been found or fixed. They've run hundreds of simulations and spent millions of dollars. They still can't get the ice in the fuel lines to clog the fuel oil heat exchanger and cause the kind of blockage that brought down Flight 38.
We came to a stage where we had not actually come up with what had caused this accident. At this time, the media and also the general public, there was a bit of unrest as to why we had not yet come up with an answer.
Industry pressure to resolve this case is intensifying. Investigators still need to know what made Flight 38 different from thousands of others that had flown under similar conditions. To find out, they retrace every moment of Flight 38's journey. The voyage from Beijing involved a gradual climb, a steady cruise, and a gradual descent. The fuel temperatures fell and rose accordingly, causing ice to accumulate in the fuel lines. That ice posed no danger unless it was released. Now investigators study the fuel flow and find that it was kept steady for most of the flight. The autopilot maintained constant speed and low power for hours, never demanding an abrupt increase in engine power until just before they reached the runway.
The approach into Heathrow was quite a turbulent approach, and the engines were demanding various levels of thrust power.
It's not me, that's the auto throttles doing their thing.
And there were 4 changes in fuel flow, one of which was a very high fuel flow of around about 12,000 to 13,000 pounds per hour demanded.
A closer review of the American Delta flight reveals that its engine rolled back under the same circumstances, a sudden demand for power after a long period of consistent speed. Investigators are now set to duplicate these precise conditions. They hope that by reproducing the moments just before landing, which was the only part of the flight where the crew suddenly required more power, they may finally get the answer they're looking for.
The problem that we were looking at is very, very difficult to replicate. And during what was one of the last tests, we actually managed to get all the elements together.
After simulating running engines at constant speed, investigators increased the power.
We allowed the ice to accumulate for 3 hours, and then the flow rate was increased.
What happens next breaks the case wide open. In Boeing's Seattle lab, investigators' sudden demand for more engine power causes the fuel pressure downstream of the fuel oil heat exchanger to drop dramatically. And when investigators examine this vital component,
we then saw that ice had formed across the face of it.
soft ice that had formed deep inside the fuel lines broke free when the pressure was abruptly increased. It restricted the flow of fuel to the engines. Investigators have finally found the Achilles heel hidden deep inside the 777. The tubes that bring the fuel through the FOHE jut out just above the container of hot oil. It's just a few millimeters, but was enough to prevent the ice from coming in contact with the hot surface below and melting.
Now, the ice doesn't totally restrict the fuel flowing through it. It has some porosity, so the fuel will continue to flow through. But the flow rate is much slower than it should be.
In all of the tests, only one gave investigators the result they were looking for, the one that exactly matched the journey of Flight 38. While the plane flew over Russia, water in the fuel turned to ice. At -20, it began to build up along the inside of the pipes. The steady speed of the aircraft ensured this accumulation was never interrupted. Then, as the plane approached Heathrow, turbulence resulted in the first demand for power since much earlier in the flight, and things cascaded into a serious problem.
Doing their thing. You might want to keep the autopilot on a little longer than usual.
The gushing fuel washed the ice through the fuel system until it built up against the face of the FOHE, with disastrous results.
Pete, I can't get power on the engines. It's not giving me power.
Facing a threat no one knew existed,
Mayday! Speedbird!
the pilots didn't have a chance to solve the problem. But why had the American Delta crew been able to clear the blockage, while the British Airways flight ended in near catastrophe? It's discovered that after just a few seconds of reducing engine power to idle, the blockage in the FOHE clears. But this maneuver was not available to the British Airways pilots because they were so close to the ground. Soon after the Seattle tests, Rolls-Royce redesigned the fuel oil heat exchanger.
So what Rolls-Royce did was to actually remove those protruding tubes so you now have a flush face.
And they found that if they flattened this surface, even if ice crystals did form in the fuel, they'd go straight down the holes in the block. Very, very easy fix.
Other aircraft manufacturers are ordered to ensure that their systems aren't vulnerable to the same problem. Peter Burkill, John Coward and the rest of the crew of Flight 38 received the British Airways Safety Medal for their performance during the accident. It's the company's highest honour.
Crew have been presented with an unprecedented failure, and they did the best they could in the time that they had available.
The crew did as good a job as they could, and since they really only had about 30 seconds to think about what they were going to do about this, they couldn't have done any better than they did.
The ice that brought down one of the world's most sophisticated airplanes was gone by the time investigators showed up.
Weird thing about this investigation was that the culprit had fled the scene.
The inquiry into what happened consumed thousands of hours of manpower and cost millions of dollars.
These people really pulled out the stops to find out. And the reason? We have to know.
With unrelenting diligence and a little inspiration from Sherlock Holmes, the mystery was finally solved.
Whatever is left, however improbable, must be the cause.
Brand new air crash investigation is back next week with the story of the pilot who landed in New York's Hudson River. Stay tuned for more drama in the skies.